Hi guys, so today we're going to be looking at circular motion and specifically centripetal force and acceleration. Now I've got with me today a special guest, Mr. Monkey. Yeah, sorry, that's his name. I haven't named him yet. Can you believe that? I've had this monkey for, how long have I had you? Like 15 years and I haven't given him a name yet. So if you want to help give me a name for Mr. Monkey, maybe next time I do this video, he'll actually have a name. But for now, Mr. Monkey is going to be joining us today. All right. Now, the first thing we're going to do is we're going to have Mr. Monkey is a special monkey, not just because he loves physics, but because he can fly. Watch this. There he goes. See, there goes Mr. Monkey, and he can fly in a circle just like this. You notice that he's going in what we call uniform circular motion. It's uniform circular motion because I'm keeping the radius, the length of my string is staying the same. So the radius is constant. And he's going more or less at a constant speed as best as I can. So that is uniform circular motion. Now, what I'd like for us to do is draw a couple of pictures, a free body diagram, and try to explain a little bit more what's going on. And we'll do some calculation stuff here as well. All right, so the first thing is free body diagram. So I'm going to draw a picture of what's happening from above, right? So here's me. I'm in the middle. This is Mr. B. I'm going to put some hair on there because I'm not quite bald yet, unlike my poor father. I should probably edit that out. Anyway, so I am holding Mr. Monkey, and there's Mr. Monkey who is being swung around in a circle just like that. All right. Now, the question is, what are the forces acting on Mr. Monkey right here? Okay, now we are going to ignore air resistance. Okay, so what are the forces acting on the monkey right here? Now we do have some vertical forces, right? This is an aerial view, so gravity is actually going to be pushing down on the monkey. You're going to have, the string is going to be pulling up just a little bit to counteract that gravity. So we are going to have those forces, but we're not going to be able to see those from this perspective. We can draw that in a slightly different perspective later if we want, but for now we're going to go with this. I'm more interested in the circle. So what are the forces in this plane? Does there need to be a force pushing forward here, right? This is the direction the monkey's moving this way in the circle. Does there need to be a force pushing the monkey forward? And the answer is no, right? The monkey should just move in a straight line. Newton's first law says he'll go in a straight line unless something makes him not. He'll continue, maintain his state of motion. So therefore, he doesn't need anything to push or pull him forward. He's going to move forward because that's what he does, right? Now, the only thing here that I can see that's contacting Mr. Monkey is the string. Now, the string is going to exert a force in this direction. Now, we normally call a force of a string tension. And so the tension of the string is actually pulling the monkey towards me. Now, that should kind of make sense, right? Because Newton's first law says that the monkey should just go in a straight line. But he doesn't. He gets pulled over in this direction, so that he curves like that, kind of like gravity pulling an object down, right? That's tension is the object that's pulling it over in this direction. Now, as it goes around, its new direction of motion is always kind of pointing in a different direction. Once I get up here to the top, the monkey would be moving in this direction. And again, my tension will pull kind of downward, causing it to come downwards and stay in that circular motion. Now, what that means is, what is causing the monkey to go in the circle is the tension. Without that tension, the monkey would just continue to go in a straight line. Of course, gravity would pull him down, but from this perspective, he would continue in that direction. Now, because tension is the force in the direction of the radius that is causing the circular motion, then we say that tension is the centripetal force. That's going to be really important when we're looking at things going in circles, is identifying what is the force or the forces that are causing something to go in that circular motion. What is the centripetal force? Now, let's see if we can put a little bit of math with this, all right? The first thing I'm going to tell you is that the length of my string is 1.5 meters. Now, if the length of my string is 1.5 meters, how far does the monkey travel around the circle? What's the total distance? Now, hopefully you're looking at that and you're saying, oh, so the 1.5 is my radius. And then I've got the circle there. So radius to get not the diameter, the circumference of the circle, I need to do circumference, which is the distance around the circle, is going to be 2 pi r. You've seen that before. You know how to get the circumference of a circle. And so we just take those numbers, 2 times pi times r, the r being 1.5, and we calculate the distance around the circle. So let's do that. All right, and I get about 9.4. Now, this was in meters, which means my final distance should also be in meters. So now we've got the distance around the circle. Now, with that distance around the circle, if we know the amount of time it takes to go around the circle once, you may remember that that's called the period. If we know that time, then we should be able to calculate how fast Mr. Monkey is moving. So if I tell you that it took approximately 1.2 seconds to go around the circle, to swing around once, then we should be able to calculate the speed. Now, actually, I used a capital T here for the period because it's a time, but it's a very specific time. It's the time that it took to complete one full cycle. And so we call that the period. We use a capital T for that, 1.2 seconds. Now, we know that speed is equal to distance over time. So the distance of one circle is 9.4 meters. The time of one circle is 1.2 seconds. And so if I do 9.4 divided by 1.2, I get 7.8 meters per second. And that's the speed of him going around the circle. Now, this is important because the speed is going to connect to the centripetal force and the centripetal acceleration. I'm actually a little bit embarrassed because I gave you this nice little formula sheet in class, and I told you that every formula you needed, every equation you needed for the rest of the year was on here. And day one, we already have one that I forgot to put on there, which is the centripetal force and the centripetal acceleration. So I'm going to go ahead and give you those equations right now. You can add those onto this sheet. For the most part, I'm going to ask you not to add things on there because these are the things that you're going to be allowed to use on an assessment. Okay, but you can add centripetal force, centripetal acceleration. Now, the first thing that I want to make sure to reiterate is this. Centripetal force is not a new kind of force. Okay, it's not different from the normal force or the tension or the friction, right? Those are all forces. The centripetal force will always be one of those forces or a combination of those forces or a part of those forces. And so like you saw in this one, centripetal force is not a new force. The tension was the centripetal force here. The centripetal force is just a general term that we use to say the force is going in a circle, causing it to go in a circle. Kind of like before we said net force. And the net force wasn't a type of force, it was just putting all those forces together, and this is the result. So when something's going in circular motion, we say there is a centripetal force, and the centripetal force is just tension, normal force, friction, whatever it needs to be, whatever's causing it or allowing it to go in a circle. All those forces acting in a direction that we call radially. Okay, so centripetal force, the equation for that is this. Okay, now you've seen most of those variables before. Centripetal force is equal to the mass of the object times the velocity squared, or the speed. We're going to use speed here, and then divided by r, which is the radius of the circle that the object is going in. All right. Now, this will very often be connected to other forces. If you know the value of the tension, then maybe you put the value of the tension in there in this situation. In other situations, if friction is the centripetal force or gravity is the centripetal force, then in all of those situations, we may be able to make connections between this equation and other force equations. And so one of the most important things that you will do in these questions is identify what is the centripetal force, because sometimes you'll be able to find that in a different way that will allow you then to work with this equation here for the centripetal force. We'll see some of that as we go forward. The other equation that I want you to have is for the centripetal acceleration. Now, I almost feel like this one isn't necessary because you already know that force is equal to mass times acceleration, right? So if force equals mass times acceleration, you just divide both sides by the mass and you get the acceleration. So in this equation up here, divide both sides by mass, and what you'll be left with is the acceleration. The acceleration is just v squared over r. All right, so both of those things may be important as we go forward. It's just ways to describe with a magnitude how strong is the force causing it to go in a circle. That will be more important in some situations than others, and we'll see it as we go along. All right, now in this situation, I would like for us to find the centripetal acceleration of Mr. Monkey. Now, we are accelerating, right? Acceleration, remember, is any time that we are changing velocity, we are accelerating. So even though we're in uniform circular motion here, right? It is a constant speed going in a circle, constant radius. Even though the speed is constant, there's still acceleration, because acceleration is a change in velocity, and velocity has magnitude and direction. So if the direction is changing as we go around the circle, then our velocity is changing, and so therefore there must be acceleration. The other thing, remember, is we definitely have an unbalanced force here, and F equals ma. If there's an unbalanced force, there must be acceleration. That doesn't mean speeding up. It just means the velocity, either the magnitude or the direction, needs to be changing. All right, so here we go. We'll go ahead and calculate the centripetal acceleration of Mr. Monkey, which will be the speed, which we found was about 7.8, and then divided by the radius of our circle, which we said earlier was 1.5. And we should just be able to put that straight in. So 7.8 squared divided by 1.5. So I get 40.6. What are the units? Well, it's still acceleration, right? It's still acceleration. Acceleration is meters per second squared. All right. Now, a little bit of a challenge for you. If you are interested in pursuing physics a little bit further, one of the things that you want to be able to do is something called dimensional analysis, work with the units. So what I would encourage you to do if you are looking to take this further, or even if you're going to go further with chemistry or bio, any of those sciences, look at the units here, velocity being meters per second and the distance being in meters, and see if you can show that the units end up being meters per second squared. Now, for some of you, you really don't care, and that's fine. I get that. Just understand that if we put in meters and we put in seconds, if we put everything in SI like we're supposed to, we end up getting meters per second squared. All right, the last thing will be the centripetal force. What is actually the strength of that force needed to be able to go in a circle? How much tension is needed? How strong does my string need to be? Well, we can get that by doing mv squared over r. We will need the mass of the monkey, which is about 300 grams or 0.3 kilograms. And so we'll just go 0.3 times v squared over r. Now, you may have noticed that, oh, I already did that. That's this number right here. So yes, you could just do 0.3 times 40.6, force equals mass times acceleration. That's still valid. Okay, so yes, that is totally fine if you want to do that, or you can type everything in just the way that it is, and we should get about 12.2. Force is still newtons, and that is the amount of tension in the string. All right, so I hope that was helpful as an introduction. We're going to do one more example here of a car going in a circle, turning in a circle. So give me just a minute to erase what I got here, and we'll start with that. All right, so now let's look at a situation where we have a car. Okay, just a normal everyday car. It can be your car at home, your Nissan Xterra or Pajero or BMW, whatever you got at home. Okay, your dune buggy, it doesn't matter. So your car that is going in a circle. Okay, we're not talking about a loop-the-loop. We're just saying, you know, a road that's a circle. Maybe it's a racetrack. Maybe it's just you driving circles, doing donuts out in the parking lot. Whatever it is, your car is driving in a circle, which means constant radius at constant speed. All right, the first thing I would like for us to do is draw a free body diagram in two different points of views. The first is kind of like what we did for the monkey, is looking from above. All right, so looking from above, we know that the car is going in a circle like this. Okay, there's my car. What are the forces acting on my car? Again, we're going to ignore air resistance. Okay, we're always going to ignore that unless I tell you otherwise. So what you may say, let's say that the car is going around in this direction right here. So what you may say is, well, I think that there's got to be some type of force pushing forward. Yep, there's some friction between the tires and the ground that is probably pushing it forward. Okay, you may say, I think there's some kind of force pushing backwards. There's probably some type of friction or resistance force pushing backwards. The next question is, well, if those were the only forces, then Newton's first law would apply. Those would be balanced. It would continue at a constant speed in a straight line. What is the force that's causing it to go in a circle? Well, you may remember that we talked about this when we talked about things that go, is that in order for it to turn, there needs to be a frictional force that will be pushing in that direction. So we actually have a lot of different frictions doing a lot of different things here. These two are going to be balanced and essentially cancel out. This is the one that matters. Okay, without this friction, if you're driving on ice or gravel or something like that, you do not go in a circle. You continue to go in a straight line. Okay, you need to have enough friction that it allows you to turn. All right, now I also want us to do a picture of what's happening to the car, looking at it from behind, just because I want us to be able to look at different perspectives. So here's the car. If you need a little bit of perspective, there's the tires, there's the license plate, here's the road. The car is going this way into the page, and it's going to go into the page, and eventually it's going to come out this way. It's kind of going in a circle this way. Okay, so we're looking from behind it. If we were to look from above, we'd see this right here. Okay, so what are the forces acting on it there? Now, hopefully you've got the force of gravity. Now, this is the first time in this video that we've had a normal force, right? There hasn't been an additional contact force there. This is the first time that we're actually going to have a normal force there, right? A vertical normal force between the ground and the car. Now, the last thing that we want is, we can see this from the side as well, is that friction has to be going this direction. If friction is not going that direction, the car will continue in a straight line into the page. The friction is what allows its velocity to change its direction. So there we go, we've got friction there. Now, having done that conversation, what is the centripetal force here? Hopefully, you said that friction is the centripetal force. Friction is the force that's allowing it to go in a circle. Without that, it wouldn't. Friction is the only force that's pointing towards the center of our circle, which allows that to happen, that circular, uniform circular motion. Okay, now let me give you a little bit of information. Let's see if we can do some calculations and maybe extend this into some things that we've done before. The first thing I'll give you is that the track is about a mile, which is 1.6 kilometers. So the distance around the track is 1.6 kilometers. All right. The time it takes the car to go around the track once is about 25 seconds. Now, hopefully, you're recognizing that I use that big T. What does the capital T represent? It represents the period right? The period is the amount of time it takes to complete one full cycle. So therefore, we've got the period being 25 seconds. And now we should be able to calculate the speed of the car, assuming that it's constant speed, which I did say constant speed all the way around, not constant velocity, because the direction is always changing, but constant speed. Now, constant speed, we know that speed is equal to distance over time. Notice that this is in your formula packet, right? I'm not going to use any equations that are not in your formula packet unless I tell you to add them into your formula packet. All right, so we got speed equals distance over time. My total distance is 1.6 kilometers, which I don't want kilometers, I want meters. So there's 1,000 meters in a kilometer, so I can do 1.6 times 1,000. So 1,600 meters divided by that 25 seconds. And so when I go 1,600 divided by 25, I get 64 meters per second, which is pretty fast. It's a reasonable speed. All right. So we got the speed of the car. So now the question is, what would be the centripetal force on the car? Now, in order to do that, we do need a mass. So in your packet, I tell you that the mass of the car is, the mass of the car is 2,000 kilograms. So let's go ahead and put that all together and calculate the centripetal force. We could get the centripetal acceleration, but I'm not going to worry about that right now. So we are going to get centripetal force. So centripetal force equals the mass, which is 2,000, times the velocity, which we just found was 64 meters per second, v squared over r. Remember, r is the radius of the circle. I don't have that. I actually have the distance around the track. So I'm going to need to do a little bit more math here before we move on to that. So we found out that the total distance around was 1.6 kilometers or 1,600 meters. We're going to have to go back to the circumference is equal to 2 pi r. This time I know the circumference, which is 1,600 meters. And so I'm going to have to calculate r there. So I'm going to divide that 1,600 divided by 2 and then divided by 3.14. And I'm going to get about 255. So my radius is 255 meters. So please, please, please remember that r is the radius of your circle, and you may have to get that using your information about circles, circumference, and things like that. Okay, so we've got the r there, so that's 255. Now everything's in meters, everything's in seconds, everything's in meters per second, right? Everything's in SI units. So when I go take all these numbers and plug them in, then I'm going to get a very large force, and that's okay. It's a very large car, 2,000 kilograms, 32,125 newtons. All right, so force, I put an extra number in there, 321, sorry. My brain was working faster than my hand. There you go, 32,125. Okay, so awesome. We've now connected this to the idea of circular motion. We've talked about uniform circular motion. We've talked about period. We've talked about centripetal force, which in this case was friction. Remember with the monkey, Mr. Monkey going around the string, the centripetal force was the tension. So centripetal force is not a new type of force. It's just a label that we give to the forces that are causing the circular motion. Not anything causing the speeding up, slowing down, just what's causing the circular motion, anything in the radial direction. Okay, now the last thing I want us to do is, can we find out how much friction there is? Okay, more specifically, can we find out the coefficient of friction between the tires and the ground? What is the minimum coefficient of friction that must be there in order for this to work? Okay, now what I'm going to remind you, if you look at your formula packet, the formula sheet that I gave you in class, is we know that friction is equal to the coefficient of friction times the normal force. Okay. Now, what we said earlier was that friction is the centripetal force. And guess what? We just found the value of the centripetal force. So if we know the value of the centripetal force, then we also know the value of friction, because friction is the centripetal force. And so here, friction is going to be 32,125 newtons. Now, I'm not going to put the units on there. Then we've got the coefficient. Now we need the normal force. Now the normal force, we're going to come over here and look at our free body diagram. Remember, our normal force is going to have to equal gravity here so that my car doesn't take off the ground or dig into the ground. So it's going to be equal to the force of gravity. And remember, force of gravity, again, you can look at your sheet if you need to, but the force of gravity is equal to the mass times g. So the mass was 2,000 and g was 9.8. So I'm going to go 2,000 times 9.8, and I get 19,600. And so now I should be able to solve by doing that 32,125 and dividing by 19,600. And I get 1.64 is the coefficient of friction. And so we were able to now connect this idea to some of the other things we've done. This is the goal of this year, is that everything is interconnected. Yeah, we're talking about circular motion, but it's going to be combined with your forces, your free body diagrams. Hopefully we'll get into some kinematics later and some energy stuff. It's all going to be there. All right. So that's it for this video. I do want to recognize that this is a little bit high. So this probably, most of you, if you remember from your stopping distances project, normal coefficients of friction between the ground and a tire are, 0.5, 0.6, 0.7, maybe even up to 0.8 or 0.9. You're probably not going to go get a coefficient this high. So in this situation, you're probably not going to be able to accomplish this with your normal everyday car. However, what you might be able to do is, if you have a car with racing tires might be able to get you up to this coefficient of friction. So you'd actually have to change the tires, possibly change the track that you're driving on. But yeah, this is a pretty high coefficient that would be necessary in order to be able to go this fast around a track of that size. Okay, and that's it for today. And I hope that's a good introduction for you to circular motion. See you next time.